Hello dear students, welcome to Math Root. In this lecture, I am going to talk about a very important proposition that is very related to power series. Proposition: let f of z equal to summation n from 0 to infinity n into z minus a whole raised to n have radius of convergence are greater than 0. Okay. Suppose this power series have the radius of convergence r. Okay. A positive number r. Then first statement, for each k greater than or equal to 1, this series summation n from k to infinity n into n minus 1 into etc. n minus k plus 1 into n into z minus a whole raised to n minus k has radius of convergence r. That means for any k greater than or equal to 1, the power series have the same radius of convergence. Okay. That means this is the derivative of this power series. Okay. That means power series and its derivative have the same radius of convergence. Okay. Statement B, the function f is infinitely differentiable on the set BAR, and furthermore f raised to k of z is given by the series star for all k greater than or equal to 1 and mod z minus a less than r. That means this function f, that means this power series is infinitely differentiable on the set BAR. That means the open ball with the center a and radius r. Also, derivative of all order f dash of z, f double dash of z, etc. Derivative of any order is given by the series this. And these derivatives are valid in the region mod z minus a less than r, that is the region with the center a and radius r. See, for n greater than or equal to 0, n equal to 1 by n factorial into f raised to n of a. We have a0, a1, a2, etc. There are so many terms that is defined by n equal to 1 by n factorial into f raised to n of a. Okay. Proof: assume a equal to 0. That means the power series with the center 0. Okay. Center origin. Then f of z equal to summation n from 0 to infinity n into z minus a becomes 0, z minus 0 whole raised to n. That is equal to summation n from 0 to infinity n into z raised to n. Okay. Statement 1, proof for statement A. We first remark that if statement A is proved for k equal to 1, then the case k equal to 2, 3, etc. will follow. Okay. So, we prove for k equal to 1. Okay. So, we have for k greater than or equal to 1, summation n from k to infinity n into n minus 1 into etc. into n minus k plus 1 into n into z raised to n minus k. Okay. Put k equal to 1 in this expression star, we obtain summation n from 1 to infinity n into z raised to n minus 1. Okay. Note that for k equal to 1, the derivative of this power series, that means the derivative of this function is given by summation n from 1 to infinity n into z raised to n minus 1. From the definition of radius of convergence, 1 by r equal to limit n tends to infinity mod n all raised to 1 by n for the series summation n z raised to n, and 1 by r dash equal to limit n tends to infinity mod n all raised to 1 by n for the series summation n z raised to n minus 1. Okay. So, we have the radius of convergence for this series is given by 1 by r equal to this formula, and the radius of convergence of this power series is given by the formula 1 by r dash equal to this. Okay. We want to show that the radius of convergence of these two power series are the same. That means we want to show that 1 by r equal to 1 by r dash. That means r equal to r dash. So, our claim is r equal to r dash. To prove the claim, we have to establish that limit n tends to infinity n raised to 1 by n equal to 1. That means nth root of n, limit of nth root of n equal to 1. Okay. If we show this condition, then limit of this and this terms are the same. Okay. So our claim is r equal to r dash. To prove limit n tends to infinity, n raised to 1 by n equal to 1, use Cauchy's theorem on limits. Cauchy's theorem on limits says that if sequence un is a sequence of positive constants, then limit n tends to infinity, un raised to 1 by n equal to limit n tends to infinity, un plus 1 by un. Okay. Then we obtain limit n tends to infinity, n all raised to 1 by n equal to limit n tends to infinity, n plus 1 by an. We have the power series f of z is equal to summation n from 0 to infinity an into z raised to n. Okay. So we put un n instead of un. Okay. Then limit n tends to infinity, n raised to 1 by n equal to limit n tends to infinity, n plus 1 by n. Okay. That means here this sequence n is equal to n. Okay. Here the sequence n equal to n. So limit n tends to infinity, n plus 1 by n equal to limit n tends to infinity, n by n, that is equal to 1 plus 1 by n. Okay. Limit n tends to infinity, 1 plus limit n tends to infinity, 1 by n. Limit n tends to infinity, 1 by n becomes 0. Okay. Then limit n tends to infinity, 1 equal to 1. So we obtain that limit n tends to infinity, n raised to 1 by n equal to 1. Okay. So r equal to r dash. So the radius of convergence of the power series and the derivative of that are the same. Okay. B part. Let capital R be the radius of convergence of the power series summation n from 0 to infinity and z raised to n. It will be shown that f of z is analytic in the domain mod z minus 0 less than r. That means f of z is analytic in the region mod z less than r. Consider the power series this. Let r be the radius of convergence of this power series. We will show that f of z, that means this power series, is analytic in the domain mod z less than r. Okay. Also note that the radius of convergence of the power series summation n from 0 to infinity n and z raised to n minus 1. The first term being 0 is also r. That means this power series is nothing but the derivative of this. Okay. So note that we already proved that these two power series have the same radius of convergence. Okay. So the radius of convergence of this power series is r. Also radius of convergence of this power series is also r. Okay. In the next step, we just put n equal to bn. Okay. We just put n equal to bn. Okay. So we just put n equal to bn. Okay. Then we have mod bn all raised to 1 by n equal to mod n all raised to 1 by n. This is equal to n raised to 1 by n into mod n all raised to 1 by n. Okay. Taking limit supremum on both sides, limit supremum of mod bn all raised to 1 by n equal to limit supremum of n raised to 1 by n into mod n all raised to 1 by n. This is equal to limit supremum of mod n all raised to 1 by n. Since limit n raised to 1 by n equal to 1. Okay. So limit supremum of mod bn all raised to 1 by n equal to limit supremum of mod n all raised to 1 by n. Okay. Claim f of z is analytic in the domain mod z less than r. Okay. We will prove that f of z is analytic in the domain mod z less than r. Take a point z in the domain mod z less than r. Okay. Let z be any point of the domain mod z less than r. Here is the domain mod z less than r. That means mod z minus 0 less than r. That means region with the center 0 and radius capital R. Okay. Z is any point on the domain. Then there exists a positive number rho there exists a positive number rho such that mod z less than rho less than r. Okay. Take z plus h any point, take a point z plus h any point such that modulus of z plus h is less than or equal to rho less than r. Okay. So that z plus h is also a point of the domain mod z less than r. Okay. So we choose a point z plus h. It is also inside in the domain mod z less than r. Okay. Which also satisfies this condition. Okay. We now have f of z plus h minus f of z by h minus summation n from 0 to infinity n and z raised to n minus 1. That is equal to summation n from 0 to infinity n into z plus h all raised to n minus summation n from 0 to infinity n into z raised to n divided by h minus summation n from 0 to infinity n and z raised to n minus 1. We know that our definition of f of z is equal to summation n from 0 to infinity n into z raised to n. So f of z plus h equal to summation n from 0 to infinity n into z plus h all raised to n. Okay. We just put definitions of f of z and f of z plus h here. Okay. F of z is equal to this. Okay. F of z plus h equal to this. Okay. So next we are going to split this summation into two. Summation n from 0 to infinity become summation n from 0 to k and summation n from k plus 1 to infinity. Okay. So summation n from 0 to k, this plus summation n from k plus 1 to infinity, this minus summation n from k plus 1 to infinity, this is equivalent to this. Okay. We just put this equation as equation number 1. Okay. Since summation n from 0 to infinity n and z raised to n minus 1 is convergent, there exists by definition a positive integer m1 such that for every k greater than or equal to m1, modulus of summation n from k plus 1 to infinity n and z raised to n minus 1 less than epsilon by 3, epsilon being a given positive integer. We just put this equation as equation number 2. Okay. We know that this power series is convergent, then by definition there exists a positive integer m1 such that for every k greater than or equal to this positive integer m1, this condition satisfied. Okay. That means modulus of this summation is strictly less than some number epsilon by 3, where epsilon being a given positive integer. Now we have z plus h all raised to n minus z raised to n can be written as z plus h minus z into z plus h all raised to n minus 1 plus z plus h all raised to n minus 2 into z plus etc plus z raised to n minus 1. Okay. Dividing with z plus h minus z on both sides. Okay. So we obtain left side as z plus h all raised to n minus z raised to n divided by z plus h minus z, which is strictly less than modulus of, if we applying modulus, okay, this is strictly less than, okay, we are applying modulus this, that is less than or equal to modulus of each and every term. Okay. So this is strictly less than modulus of z plus h all raised to n minus 1 plus modulus of z plus h all raised to n minus 2 into mod z plus etc plus mod z raised to n minus 1. Okay. We know that mod z plus h is strictly less than rho. Okay. So mod z plus h all raised to n minus 1 is also strictly less than rho raised to n minus 1. Okay. So mod z plus h all raised to n minus 1 become strictly less than or equal to rho raised to n minus 1 plus this is rho raised to n minus 2 into we know that mod z is also less than rho. So this is can be replaced as rho plus etc. plus rho raised to n minus 1. So rho raised to n minus 1 plus rho raised to n minus 2 into rho, that's equal to rho raised to n minus 1 plus etc. plus rho raised to n minus 1. So n terms, there are n terms, so n times rho raised to n minus 1. So z plus h all raised to n minus z raised to n divided by z plus h minus z strictly less than n times rho raised to n minus 1. Okay. So we have the inequality. So z plus h minus z become h. Okay. Multiplying on both sides with an and taking modulus, we obtain the inequality modulus of an into z plus h all raised to n minus z raised to n divided by h less than or equal to n into mod an into rho raised to n minus 1. As the series summation n from 0 to infinity n into mod n into rho raised to n minus 1 is convergent, there exists a positive integer m2 such that for every k greater than or equal to m2, modulus of summation n from k plus 1 to infinity n into mod n into rho raised to n minus 1 strictly less than epsilon by 3, and hence also modulus of summation n from k plus 1 to infinity n into z plus h all raised to n minus z raised to n divided by h strictly less than epsilon by 3. We just put this inequality as question number 3. Okay. This series is just convergent, so there exists a positive integer m2. Then for every positive integer k greater than or equal to this integer, this condition satisfied. Okay. That means summation modulus of summation of this quantity is strictly less than some epsilon by 3. We know that summation of this quantity is strictly less than this quantity, hence this implies this. Okay. Let now m equal to maximum of m1 comma m2. Okay. That means choose m as the maximum of m1 and m2. We have from equation 1 taking m for k and making use of equation 2 and equation 3. Okay. Then modulus of f of z plus h minus f of z by h minus summation n from 0 to infinity n an z raised to n minus 1 less than or equal to modulus of summation n from 0 to m n into z plus h all raised to n minus z raised to n divided by h minus n z raised to n minus 1 plus modulus of summation n from m plus 1 to infinity n into z plus h all raised to n minus z raised to n divided by h plus modulus of summation n from m plus 1 to infinity n and z raised to n minus 1. Okay. Taking modulus on both sides of the equation number 1, we obtain an inequality like this. Okay. So here we take summation n from 0 to m instead of summation n from 0 to k, because we choose m as the maximum of m1 and n2. Also we use this summation n from m plus 1 to infinity instead of summation n from k plus 1 to infinity. Okay. We found two strict inequalities for these two modulus. Okay. So this implies this modulus strictly less than this modulus plus epsilon by 3 plus epsilon by 3. Okay. Also because n into z plus h all raised to n minus z raised to n divided by h converges to n and z raised to n minus 1 as h tends to 0. Okay. And this modulus, that means this modulus is the sum of a finite number of terms. Sum of a finite number of terms. We see that there exists a positive number delta such that for mod h less than delta, this sum is strictly less than epsilon by 3. That means this sum is strictly less than epsilon by 3. Okay. So this modulus is strictly less than epsilon by 3 plus epsilon by 3 plus epsilon by 3. That means this sum is strictly less than 3 into epsilon by 3. That means this sum is strictly less than epsilon. Okay. So this implies modulus of this strictly less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, that is equal to epsilon. That means modulus of this strictly less than epsilon. That implies limit h tends to 0 f of z plus h minus f of z by h equal to summation n from 0 to infinity n and z raised to n minus 1. Okay. Hence f of z is derivable in the domain mod z less than r. Okay. Also f dash of z equal to summation n from 0 to infinity n and z raised to n minus 1. So that f dash of z is given on term by term differentiation of this series for f of z. That means if we want to find the derivative of the power series, then we can term by term differentiate that power series. Okay. Thus this function f of z, that means the power series f of z is analytic in the domain mod z less than r. Okay. This is the proof. C part. From part A, we know that f raised to k of z, that means kth derivative of the function f of z. F raised to k of z equal to summation n from k to infinity n into n minus 1 into etc. into n minus k plus 1 into n into z raised to n minus k. That is equal to k factorial into a k plus 1 factorial divided by 1 factorial into a k plus 1 into z plus k plus 2 factorial divided by 2 factorial into a k plus 2 into z square plus etc. Okay. This expression is valid inside the circle of convergence of f of z. That means this function f raised to k of z is valid. That means this expression is valid in the circle of convergence of f of z. Okay. Put z is equal to 0 in the expression, we obtain f raised to k of 0 equal to k factorial into ak. That means f raised to k of 0 equal to k factorial into ak plus this into 0 plus this into 0 plus etc. These all terms are 0. We obtain f raised to k of z is equal to k factorial into ak. Okay. That means ak equal to f raised to k of 0 divided by k factorial for k equal to 0, 1, 2, 3, etc. Next, an important corollary. If the series summation n from 0 to infinity n into z minus a whole raised to n has radius of convergence r greater than 0, then f of z is equal to summation n from 0 to infinity n into z minus a whole raised to n is analytic in VAR. Okay. If the series, this power series has the radius of convergence r greater than 0, then this function is analytic in this open set. Okay. That means if this power series has the radius of convergence r, then this power series, that means the same power series, that means the same function f of z is analytic in the region with the center a and radius this r. Okay. A good example is that e raised to z. Okay. E raised to z is equal to summation n from 0 to infinity z raised to n divided by n factorial. Here note that center is 0. Okay. That means e raised to z is equal to summation n from 0 to infinity z minus 0 all raised to n divided by n factorial. That is equal to 1 plus z square by 2 factorial plus etc. Okay. This function e raised to z is analytic in C, because we know that the radius of convergence of this power series, that means this function is infinity. Okay. Radius of convergence r equal to infinity. Okay. So this function f of z is equal to e raised to z is analytic in the set f of z is equal to e raised to z is analytic in the set b 0 infinity. Okay, that means center with a 0 and a radius of convergence with infinity. Okay, this means what? The entire complex plane. Okay, point 0 0 and the infinite radius of convergence means this function f of z is analytic at everywhere. Okay, so this function is analytic in the entire complex plane. Okay.